So let's go ahead and take a look now at example number 7. In example 7, we're going to try to use the two most recent theorems that we talked about in the last video to determine where this, complicated looking function is actually continuous. So remember that we saw the following ideas in the last video, that if two functions were continuous at a specific spot, we could add, subtract, multiply them by a constant, multiply them together, or divide them, provided the bottom doesn't turn into 0, and we would still end up with a continuous function. We also saw that the following types of functions were continuous everywhere they were defined. So let's take a look down here at example number 7 and the function that we have here and start looking at the different pieces that we have. So let's start here with the numerator of our fraction. We see here we have a natural log of x. We know by itself that that piece is a logarithmic function, and so it's continuous everywhere it's defined. So the question that we would have is, where is it defined? So I'll start by saying we see that y equals the natural log of x is defined. Let's see, what numbers can I plug into a natural log and what numbers can I not? Well, if you remember what the graph of a natural log function looks like, this can of course be helpful. And remember, this is one of our graphs to know, so hopefully you do kind of already have it down or you're practicing that still. But notice that I'm not allowed to plug in the value of 0 for x or anything negative. This is only defined for positive real numbers. So I'll say here that this is defined on 0 to infinity, but notice I'm not including the 0. I'm not putting a bracket on it. Okay, let's see, where is the arctangent function defined? Well, I'll put here that y equals the arctangent of x is defined on, well, let's see, what does the arctangent function look like? Remember that the arctangent function we saw at the start of previous section had a graph that kind of looked like this, right? And it had these horizontal asymptotes that went off to the side. This function is actually continuous everywhere, or it's defined everywhere, and so therefore it's continuous everywhere. Okay, so if I kind of put this together, I can see here that there are only going to be a couple problems in the top of my fraction. I am apparently allowed to plug in any positive number I want, and the top of my fraction will always produce a value. I just have to be careful about plugging in 0 or negative numbers, because that would make the natural log not be able to spit out an answer. So what I can see here is that these functions are continuous only on 0 to infinity. So I can say that y equals the natural log of x plus the arctangent of x is continuous on the interval 0 to infinity. So I kind of found where the top of the fraction is continuous. Notice I said that if I'm using the kind of the first theorem here, if the first function is continuous on an interval and the second function is also continuous on that interval, then the sum of those is continuous on the same interval. Okay, well let's take a look then at the denominator of the fraction. We can see that y equals x squared minus 1 is continuous on negative infinity to infinity. There's no value that's a problem to plug into that function. However, since I'm going to divide these two functions, I should be careful of any value of x that makes the denominator of my fraction 0, right? That's kind of like what property number 5 up here is saying. If you're going to divide two things, make sure the bottom thing doesn't turn into 0. Okay, so we can see that this is continuous on here, but we can see that x squared minus 1 is going to be equal to 0 whenever x is equal to plus or minus 1. And so I can go ahead and state here that the top of my fraction is going to be continuous from 0 to 1. The bottom of my fraction is continuous everywhere, but I can't use -1 and 1. What I can start to imagine is a number line of all the different possible values that I can and can't use. We've already kind of seen that anything that is exactly 0 or smaller than 0 has to be removed. I can't use those portions. I can also then see that apparently -1 and +1 are bad values. Now -1 has kind of already been canceled out, but +1 was originally still in the running. And if I cancel out just +1, I can see all of the kind of good spots that I have left over, which would be things between 0 and 1 and things above 1. So I can say that f of x is continuous on the interval 0 to 1 and also 1 to infinity. I've kind of taken again out all of the bad spots. I can't let the natural log use 0 or negative numbers, and I can't let the denominator ever equal 0 here. And this is all the stuff that I'm left with. So hopefully you can see how I can use the above theorems to kind of show where a function is continuous or discontinuous. And I might be able to do that rather quickly. Of course, it really helps to know all these different types of functions, which is why when you think back in your algebra and your pre-calculus classes, why you spent so much time talking about these functions and their graphs and their domains and all of that stuff, because now we need to use that to understand ideas in calculus related to continuity.